Hello, everybody. I'm just sending out the link today. Just 1 second. Okay. Hope everybody's doing okay out there. There we go. Okay, perfect. So yesterday we did some rate law. How's everybody doing with rate law? Everybody's feeling okay about that, or this a little bit bigger? Does anybody have any questions? I think I see somebody out there. Nope. Never mind. Nobody out there. So no questions. All right. I think maybe I should do a couple of more practice questions. Otherwise, I think this is pretty much the rest of this booklet is practice questions. Is there another lesson? No, there is not. So the rest of this booklet is practice questions. So we might as well work on those today. And then we will introduce the equilibrium booklet in our next video, I suppose. This also means that we should do some sort of test of some sort. So my goal will be to have an online, probably Google form, and I just have to write it. That's the biggest trick. And write it in a way that you can do it in a Google form. That's the other trick. So let's start with these ones then. So we're going to start with practicing some quantitative concentration changes. So a first order reaction initially proceeds at a rate of 0.5 moles per liter per second. What will be the rate when half of the starting material remains? When 1/4 of the starting material remains? So a first order reaction, first order here means that the exponent is only 1. So we're talking about a rate is equal to K times the concentration. Doesn't matter what. Let's just call it A to the power of 1. So what will the rate be when half the material is there? So if this is the rate right now, what is the rate? What is this equal to if we go K equals 1/2 of A to the power of 1? And we notice that the 1/2 will can be taken out of the brackets, moved out of the brackets and over here, if we like. That might make it nice and clean. And now that the 1/2 is out of the brackets, we realize that the only way we could balance it is if we also had 1/2 the rate. So dividing your concentration by half for a linear first order reaction is going to half the rate. If we plotted out this data, we would be talking about rate and concentration. We would say that this is a linear relationship. So whenever we take if we take this as sort of 1, then when we half the rate, so this will be our half, then this will also be 1/2. This is a rate equals K times A power of 1. Okay, and so 1/4 rate will also be the result if you have 1/4 of the concentration. This is not the case if the exponent is different, right? So if the exponent is squared or cubed, any of those things, it's not going to be the same. It's going to be, in fact, quite a bit different. All right, so let's assume that N2O and O2 react according to the rate law, rate equals K times N2O times O2. How does the rate change if, and then we look at these, we take their consideration. So here we have the original rate, right? Rate equals K times N2O times O2. And if we want to keep that balance, N2O times 2O2, what do we have to do to the rate? We need to put a modifier on the rate. We can freely move this one. We have to consider any exponents, but there are none. So we are free to move that 2 around. We can treat it like it goes in the front here and get it out of that bracket. Try to remove it out of the bracket just so that we make sure. So always move a coefficient out of the brackets in this type of problem. And so the rate will have to be doubled as well. Because we have to keep them equal, right? If we want it to be equal on both sides, then it has to be, we have to say that it's equal. We have to have a 2. Remember, by substitution rules, this thing originally was equal to rate. So then that 2 means that we have 2 times the rate. The volume of the enclosing vessel is reduced by half. This one's much trickier. Excuse me. Whew. So this one's much trickier. This one depends on us remembering some details from the past. One of those details being how to calculate a concentration. So concentration is equal to moles divided by volume. I like N for number of moles, divided by volume. So what we have here in this reaction is we have rate is equal to K times N, N2O. Here, just one second, I'm going to use a little. K times N of N2O divided by a volume times N of O2 divided by a volume. So for this gas, when we reduce the volume, we increase the concentration. So let's write that out again. So we're going to write K, and it says reducing the vessel by half. So N2O divided by V over 2, and then NO2 divided by V over 2. Now this might be a challenging one for you to conceptualize if math is something you don't hook into immediately. One of the rules that we teach you in math is that if you have to divide a fraction, you will flip the fraction and then multiply. So here we have a denominator. So we have a denominator in the denominator. So both of these will be flipped and then multiplied by the value on top. So what I mean is we're going to end up making our graphic look like our equation look like this: N2O divided by volume, and then the 2 will come up to the top. I'm going to put it over here because that's pretty normal. So that's the 2. It's been flipped. Okay, now we want to move everything forward to the bracket. forward out of the bracket. So those two 2's will come to the front. 2 and 2. There's no exponents. And then K, N, NO, N2O divided by volume. NO2 divided by volume. And that is, of course, going to be equal to 4 times rate. Since at the beginning we said all of this is equal to rate. That's what we said right at the top. I think we probably want to put a spacer here. So this is one of the reasons why decreasing the volume of a reaction is a very effective way of increasing chemical rate. Whew. These mornings are hard, eh? Notice that only one of you is making it out there right now, so we'll find that rhythm. Okay. Assuming that NO and H2 react according to the rate law, rate equals K times NO to the power of 2 times H2 or times hydrogen. How does the rate change if the concentration of H is tripled? So this is the same idea. We're going to take our rate law and we're going to say K times NO to the power of 2 times 3 H2. Notice there's no exponent there, so there's an exponent of 1. So I can just move my 3 forward, move it out to the front. 3 K N O power of 2 H2, which is the same as writing 3 times rate. Since we said that in our rate law, this is rate. Okay, now let's try that again, but with NO. So notice that this is going to be a much bigger difference. So NO has been doubled, so 2 times NO squared. So that's going to be equal to, so now I have to move the 2 out of the brackets. But when I move the 2 out of the brackets, I have to take into account the square. So moving the 2 out of the brackets, I get a 4K times NO squared times H2. And so that is equal to 4 rate. So doubling the NO concentration has a larger effect than multiplying H2 by 3. So if you're thinking about controlling this chemical reaction in practice, we would want to think about controlling that NO. That's what's really going to give us the best benefit for the best increases in reaction rate. The volume of the enclosing vessel is reduced by half, so this is going to affect all of them. Lowering volume equals an increase in concentration. I showed you the math in the previous one. I think we can kind of skip through and say that, and let's just have that effect dropped in the numerator instead of dropping in the denominator. So we're going to, so reducing by half means that we're going to double the concentration of NO and double the concentration of H2. And I'm missing one important detail here. I did not include my square. Very, very important. Okay, move all of your coefficients outside of their brackets. So this is going to be a 2 from the H2 and a 4 from the NO. And now they're out of brackets, so I'm not going to write them a second time. And now I'm going to multiply, so I get 8K, since that's what's being represented between these brackets. And that's equal to 8 times the rate. So much bigger change than anything is to decrease the volume. So squeezing that reaction down, you're going to have a much higher reaction rate. And simply a concentration effect. When it comes to determining rate, there's really not much difference. It could almost be reduced down to thinking about just concentration and energy. When we think about particle size is really effective concentration. Which chemicals are, when the particles are smaller, then that means that there's a higher effective concentration because there's more particles that are available to react. When the particle sizes are larger, then there are pieces of the particles that are trapped inside. I'm trying to think of an example. I got a little ball here or something. So if this is my particle size, and then I can only touch the outside of the particle. This thing's made of sponge, right? But I can only react with the outside edge. So the effective concentration when the objects are large is low. When we break the object up, we've increased the effective concentration because we've increased the number of target sites. Yeah, so what other effects did we discuss? So changing volume just increases concentration. Heat increases energy, so that's the other component. Trying to think of all the other examples that we had. Anyways, you really need to. It's really mostly, especially in the kinetic model, it's really about concentration and energy. Okay, so for the reaction A plus 2B goes to 2C, find the rate law and calculate the value of the specific rate constant. So we can do this in a very full way, or we can do it in a shorthand way. The very shortest way is to look at the table and think about, what changes are we seeing in these two, and then what changes are we seeing in the others. Or we can do a very full explanation. I have a full page, so let's do the full one now, and we'll try to do the shorthand later. So I'm going to write out the rate law for these experiments. So I'm going to do rate law 3. Let's do. Okay, so rate is equal to concentration of A to the power of X times concentration of B to the power of Y, all multiplied by some constant. So that's the generic rate law. You got to be able to write that right away. That's really important. Now I'm looking to determine X and Y and find the specific rate constant, K. So I'm going to compare two rates. I'm going to go trial 2 and 1 first. And to compare them, one way that I've seen done is to fill in the equations as best you can for the various values. So I'm going to do, this one is going to be trial 2. So maybe, you know what I'm going to do? I'm going to fill in, I'm going to do this first. Now this is probably something that only I can do because of my tablet, because I'm going to do a little bit of sliding things around in a second. Okay, so I have all of my equations here, and what I want to do is, in the fullest explanation, I want to compare two different rates, two different rate laws as filled out as possible by dividing. So I'm going to take number 2 and 1 first, and I'm just going to divide rate 2 over rate 1 with their whole equation. So this is going to be 1.5 divided by 0.5 equals k over k. They both have k. Top one has 3.0 to the power of x and 1.0 to the power of y. 1.0 to the power of x, 1.0 to the power of y. Look for anything you can cancel. I can cancel out the k, I can cancel out the k. I can cancel out 1 to the power of y and 1 to the power of y because both of those would be exactly the same. And so then we simplify, and we're going to be left with 3 on this side, 3.0 if you like, is equal to 3 over 1 to the power of x. That's the same as writing 3 to the power of x because we're just dividing by 1. Well, that means that x must be equal to 1. Because the only thing that the only number 3 could be raised to the power of that would still equal the same base is 1. Okay, and then we rinse and repeat, but we're going to pick 2 more trials. I'm worried I'm going to run out of room, so I'm going to put a little spacer. Okay, and so then we just have to pick 2 more trials, ones that are different. It doesn't really matter which ones we pick, but I noticed that there is some similarity happening between these two. So I'm going to pick those 2. So I'm going to pick number trial 3 and 2, and I'm going to do rate 3 divided by rate 2, which is 3.0 divided by 3.0, or no, it's 1.5. And that's also equal to their values for k, and their values for y, for x, or for a, which are the same, and their values for b, which are different. Now, I do have some advantages here. I know that this is to the power of 1 now, because I know what x is, so it's not a bad idea to throw that in there, just in case it's something weird. Sometimes they're not equal. And then we solve. So we're left with a 2, 3.0 divided by 1.5 is 2, and that's equal to, well, let's just double check here. We do some little canceling here. K, 3 and 3. Okay, 2 to the power of y divided by 1 to the power of y is simply 2 to the power of y. So y must be equal to 1. Now, what if you made a mistake? Well, we took the easiest route possible. But what if we had decided to mix, instead of rates 3 and 2, what if we had done trial 3 and 1, which is totally doable. And we're going to do probably the larger rate, so rate 3 over rate 1. Then I would have had 3.0 divided by 0.5 equals 3.0 divided by, I believe it's 1.0, right? Yeah. We have some k's over here. 1.0 and 2.0 divided by 1.0 as well, I believe, right? Yeah. And these would be y, this would be y, this is be 1 and 1. Okay, So proceed as you can. Notice that we cannot cancel the a values anymore. So we just have to carry through with our calculation. So 3 divided by 0.5 is 6. And 3 divided by 1 is 3 times, and then 2 to the power of y is still 2 to the power of y. So 2 to the power of y divided by 1 to the power of y is still 2. And then, it's a little bit more algebra. You can divide away the 3 on both sides, and you're left with 2.0 equals 2.0 to the power of y. So it still works out that y is equal to 1. Okay, the final thing is to think about what is now, well, first we have to write our rate law. We haven't actually written it, so we haven't got our final mark here. So the rate law is rate equals k times a times b. Pretty boring, really. Very boring rate law. Okay, so if we want to find find k, we can pick any of our trials. I believe our very first trial is probably the easiest one to work with. So let's pick that one. So I'm going to copy that. So all I'm going to do is I'm going to go in and erase x and y, put in my rate law values, which are 1. And then I'm going to do some multiplication, and I'm going to say 1 times 1. Okay, very, very boring. This is going to be k times 1 is 0.5. We can divide by 1, but I hope that you all know that dividing by 1 doesn't do anything. So all we're left with is 0.5 equals k. Not a bad idea to go in and do a double check. So let's just pick another one. Let's pick trial 2. Trial 2 is 1.5 is equals 0.5 times 3 times 1.0. Let's just do a double check. If I multiply this out, 0.5 times 3 is 1.5. 1.5 times 1 is 1.5. So it does work. So this is just a check. If you're doing all of the work, then a check is probably the most important part, because you don't want to do all this work and then find out you're wrong at the end. Or you don't want to do all this work, submit it, and then get your mark back and realize, like, oh, I was wrong. Like, do the double check, and then you can catch yourself. Any questions out there? Maybe we should do a Google meeting in the afternoon one of these days. Maybe that would be a better time for everybody. I'm noticing that we're having some pretty low attendance in this morning. I'm just going to go to my classroom and see if what's going on. I'm going to add in a rate law assignment right now. Yeah, okay, we'll just put those on. Yeah, if you were in class lately, then you might have already got these. I don't know what we're going to do with these. We'll just throw category, topic. Can't believe it's already that time there. Okay. Can't believe it's Thursday. It's Wednesday already. It's good. This is going by pretty quickly. Okay, maybe not quickly enough though. Hopefully your time in physical isolation is not driving you crazy or anything, or not too stressful. I've been trying to get some things done. Look at this. I've got my my chimpanzee skull here. It's got a couple of still breaking away some of the supports here, but it will eventually look like a nice chimpanzee skull. I got a nice jaw on it. I'm kind of debating about pulling that jaw right off. That would make it life a little easier. There we go. So that's been keeping me busy. Hopefully you guys have also found something useful to keep you you entertained in this this trying time. Well, there we go. Yeah. I'll show it off to my bio class. I'm sure they'll be more excited about that. A couple. Anyways, it was a CT scan, so it's always exciting using some of that knowledge we gained in our energy unit, CT. Okay, let's get into this. I don't like this kind of question. This one has decimals and stuff. It's kind of pain. Okay, but we can do it. It's mostly just that the math is a pain. Nothing else about it is particularly difficult. Let's try to do this by the shorthand method. So to do it shorthand, we're just going to look for similarities in the equations and play around with those. So all I'm looking for is patterns. So noticing these two are the same and these two are different, I can use this pair. We'll be able to use to solve for x. If we're going to say this is x and this is y. So we know that our initial rate law will be rate equals k times I minus to the power of x times OCL minus to the power of y. So we can use this first pair to solve for that. We know that anytime that you have a pair where the values are similar, that means that they would cancel in that larger division equation. So what I can do is I'm going to do trial 2 and 1. And all I want to do is compare my concentration of I minus divided by my concentration of I minus. And in this case, I think we're going to go 1 on top and 2 on the bottom. And that's got to be equal to the rate 1 divided by the rate 2. And all of this has to be raised to the power of x. It's a little bit nicer way of organizing it because I know sometimes it's a little ugly to divide two things with exponents. So let's put our numbers in. We get 0.12 divided by 0.060. Power of x has got to be equal to the division of 7.91 by 3.95. You actually don't need the times 10 to the negative 2 because those will cancel out. But we'll keep them in there. 7.91 divided by 3.95 equals 2.002, so that's good enough for me. 2.0. And then this one also gives me 2 to the power of x. So x must be equal to, 1. So there we go. So there's our first one. So for the second one, I'm going to just change pens. And the second one, I'm going to look for another place, but I want to pick one where the values of I minus are the same. So I only have one option for that. I have this option here. And luckily, these two are also have an option there. And then we have some comparison we can make there. Okay, so we're going to do a trial 2 and 4. And I want to do, I can ignore the I minus. I'm only going to focus on the OCL minus. I'm going to do OCL minus. I'm going to set everything up just so I know what I'm doing. 2 over the concentration of OCL minus 1. And that'll all be raised to the power of y. Okay, so let's punch those numbers in. 0.18 divided by 0.9090, power of y, is equal to 3.95 times 10 to the negative 2 divided by 1.98 times 10 to the negative 2. I don't actually need those brackets, so let's get rid of those. Okay, so 3.95 divided by 1.98 gives us 1.99. That's pretty good. Good enough to say that it's 2. And this one will be 2 as well, to the power of y, so y equals 1. First order reactions are going to be pretty typical. This means that you essentially, depending on only the concentration of one of these rocks or whatever, one of these atoms coming into contact with the other. So we don't have to worry about the yeah, it's a direct direct link. And let's think about this. This reaction looks like it should be a 1-to-1 reaction, right? Like it looks like to me that you have an I minus, it's flying over and it's colliding with one OCL minus, probably moving slower because it's bigger or it has more molecules. It just hits it at in one reaction, and then you are left with the IO and the Cl minus. So this reaction, think about like looking at it. Looks like that somewhat. So this thing and this thing have to collide. And so because there's only a single collision in this reaction, it makes sense that the reaction rate will depend on the collision between both, will depend both on the concentration of I and the concentration of OCl. And so that's really that makes a lot of sense for the rate law to be first order with respect to both different reactants. What's the value of the rate constant, the specific rate constant? We just have to pick one set and then fill it in. So let's see one I can remember before I lose it here. So let's, we did trial 2. Okay, so trial 2 was, the rate was 1.9, or no, 3.95? Yeah, 3.95. Times 10 to the negative 2 was the rate, and that was equal to K times 0.6, it looks like. Okay, gotta double check. 0.18 and 0.06. Okay. So this is trial 2. I just picked out trial 2 at random. I didn't really think it through, just one that I could see. And so I'm gonna do 0.06 times, yeah, let's maybe do that, times 0.18. And that gives me this. I'm going to get 3.95 times 10 to the negative 2. Okay, now we're going to do some division. Now I'm worried that some of you are starting to go like, boy, this is a lot of math we're doing in this chemistry class. And I do try to make this only like one outcome. So, you know, we're gonna spend we spend 1-2 days on it. Well, that's it. That's it. I try to make everything equal. I want you to think about it like, well, let's use E, negative 2. Think about it like it's an outcome, like it's one outcome. So if you don't understand this idea, that's okay. We have, you know, 100 other ideas that I want you to understand as well. And I'm sure that those ones you already are getting. We only have we have 3 significant figures max for sure in this question. So that's going to be my K. Yeah. I think I actually have 2 significant figures because I have 2 significant figures here, 2 here. So actually I have to cut off one of those 6's, 3.7. Boy, that's a long road to go, isn't it? To get like those answers. The good news is that it is very similar every time, so it doesn't change very much between questions. So once you figure it out, which might be a big ask, but once you figure out like the approach and the method, then it really is just a matter of doing it over and over again, the same type of question. Another reason why I don't, I don't have huge expectations on this section. I think that, it's good to be able to learn an approach and a methodology and apply it to multiple times in different ways, but it's also just one, right? It's only one method, one approach. This just came off the printer this morning, so I'm still cleaning it up. Okay, how are we doing? We are at 9:40. We've got 2, 3, 4, 5. There's a lot of questions here. Let's maybe do one more together, and then maybe we'll skip over to some of the other questions. Let's skip over to question 11 after this one. So we'll do one more, then we'll skip down to question 11, and I'll try to fill in the rest as I go, and hopefully it'll be up, and then update it on the website. Okay, so for the reaction of this reaction is a generic reaction A, B, and C. Find the rate law and calculate the value of the specific rate constant. Okay. So we have we're going to look at this table, find the examples that are changing, and see how much of an effect each change has. Let's do the even shorter hand version. This can be very simple. So one way to do this is to go on the table. We got 2 to the power of x, 1 to the power of y, 1 to the power of y. And then find the difference here. What's 1.4 divided by 3.5? I think that's 4, isn't it? Yeah, it's 4 times. So these have to all be equal. So we're saying that, so on the side of the table, you just go 2 to the power of x times 1 to the power of y times 1 to the power of z, I guess, sorry. Z equals 4. So the 1's don't have any effect, so we can ignore them. 1's go away. 2 must be to the power of 2 to the power of 2 is equal to 4. So x equals 4. equals 2. That's the shortest possible way you can do these questions. Let's look and try it again. Here we have 2 to the power of now 2, or sorry, we have 1. 1 to the power of 2, because now we know that x equals 2, so I'm going to even put a little 2 up here. We have 2 to the power of y, and we have 1, and we have a change of 1. Okay, that's interesting. So that means that 1 to the power of 2 times 2 to the power of y times 1 to the power of z equals 1. Okay, we can get rid of 1 to the power of 2 is 1. 1 to the power of z is 1. 2 equals 1 if it's raised to the power of 0. So this is one that I find that almost every time I solve this question, students go, "What are you talking about?" You might have to just try it out in your calculator. 2 to the power of 0 is 1. This is an exponent thing because 2 to the power of 2 is 4, right? 2 to the power of 1 is 2, so 4 divided by 2 is 2. So now 2 divided by 2 is the same as writing 2 to the power of 0, which is 1. 1 divided by 2 is the same as 2 to the power of negative 1, which is 0.5. And it goes on for that. So 0.5 divided by 2 is the same as writing 2 to the negative 2. So the trend of exponents is that you are always, as the exponents go down, you're dividing by that base value. So 2 to the power of 0 is like saying 2 to the power of 1 divided by 2. All right, so now we have our value of y, 0. So now we just have to go and look for our value of the final one, which is c. So the only options we have, yeah, this is a good option. So if we take this one, then it's 1 to the power of 2. This one, 2 to the power of 0. And this example here, which is a multiplying by 2 to the power of z. And we can see that over here we have a multiplying of 2. So 1 to the power of 2 times 2 to the power of 0 times 2 to the power of z is equal to 2. So z must be equal to 2. So our final rate law is rate equals k times a to the power of 2 times b to the power of 0 times c to the power of 2. Of 1. 1. Thank you. Okay. Power of 1. So some extension questions that I would like you to think about. Let's do one of those right here. So which chemicals are present in the rate determining step? Well, let's say which chemicals are not present in the rate determining step. We could also propose if there is only one rate determining step, propose a possible reaction. Or propose a possible reagents. Oh, how about this? Even better. I got it. Okay. If the rate determining step is the first step and forms one intermediate product, what the first step. What is this reaction? So let's hope that you can think this through. Gonna give you 1 second. I'm gonna count to 30 in my head before I answer, just so that you can get a chance to think over what you would write as your answer. This is, to me, a fair game. This is the kind of question I'd be interested in answering on a test and things. This is also a really good type of question that we can put on a take-home assignment or take-home exam, because it's not one you can immediately look up. Some of these other questions, you can look them up easier. So they're not really appropriate for what we'll be forced to do, which is take-home tests. Or at-home tests, I guess. You're not taking them home because you're already home. Hopefully you're home. So close, everybody. Just need a little bit. Okay, so you've had a second to think about it. So now that you've thought about it, if we look at our rate law, the rate law does tell us the answer to what is missing, or what would be missing from the reaction mechanism, or from the rate determining step. And that would be reactant B. Yeah, right. Yeah, so reactant B will not be present in the rate determining step. So B, because it has an exponent, because it is zeroth order. Just 1 second. I'm just gonna talk to some children about how loud they're watching their show. Boys, what's going on with that? Okay. All right. Hopefully you didn't. Well, I mean, maybe you like Paw Patrol, but I didn't want that Paw Patrol so loud. Look, here's my skull. I got all the chunks off. This is a chimpanzee skull. Please join me in Bio 40S one day, and you too could play with this chimpanzee skull. That is pretty much ready to go. Let's go. So, okay. So, just very pleased with myself. This skull. So B is zeroth order in our rate law, so it is the one that is not present. It will not be. It's present in the reaction, right? You can't have the reaction without B, otherwise it wouldn't even be in the net reaction. But it's just not present in the rate determining step, so we don't see its presence in there. Okay, so if B is missing, and we're assuming that the rate determining step is, there's only the rate determining step to talk about, we can also use that last little thing we talked about, which is that in an elementary reaction, the coefficients are the rate law part, are going to be the exponents in the rate law. So in this case, we would say that the step 1 is going to be 2a plus c, gives us some sort of intermediate. Let's just call it I. Let's call it I1. And this is our slow step. And then let's say there's it's probably some sort of step 2, and this would be where I1 reacts with B and produces D. And probably D plus an extra A, right? because notice that we did have in our rate law, we only have one A in our net reaction, so we do actually need to balance that out. This is totally, I think this is actually a pretty doable question. It'll take me a little bit of massaging to kind of figure out what the wording should be to get you to be able to produce that sort of answer. But it is well within the grasp of what we've discussed in this class so far. So think about that. Think about, always keep thinking about what are some different factors we can solve and apply our knowledge in new ways in different parts. It looks like we're at the end of class now, so I'm going to go through and do some markups on the rest of this booklet in my during my prep today. And in the meantime, okay. But in the meantime, please try to finish the rest of the questions on this page. And I will also be posting the next booklet, which is the equilibrium booklet, for tomorrow. So tomorrow we'll try to start equilibrium. I'll try to have a quiz or something posted by the end of the week for the kinetics unit, and that'll be it. We'll be done. Okay, have yourselves a great day and best of luck out there. Stay safe, and we'll talk to you soon.